Hi, everyone. I just wanted to say welcome to the Zapata team. Thank you for joining us. We have people coming over so you can get started. And I'm going to leave. Have fun.
Okay. All right. I'm not sure if we're supposed to wait for Maria, but okay. Can everyone see my screen? Is it in the presentation mode? Sorry, Caitlin or Martha, could you confirm?
Yes.
Okay. So welcome everyone. Today at Zapata Computing, our talk will be on debunking some myths from quantum machine learning. And so to give a very quick introduction to the speakers today, it'll be myself. My name is Hannah, and I'm a quantum research scientist at Zapata Computing. But we'll also have Marta Maury, who's a quantum software engineer at Zapata, as well as Caitlin Gilly, who's our quantum applications consultant. And so from this slide alone, you can see that all three of us play quite different roles as Zapata Computing, but we all contribute to QML research and applications and from different perspectives. And so before diving into the myths themselves, I wanted to talk about how Zapata Computing views quantum and machine learning, where we view the two fields like being like oil and vinegar versus oil and water, because as you know, oil and water don't really mix well, but on the other hand, oil and vinegar, under the right conditions and with some additional spices, and if you mix it right, at least temporarily, you can produce a very delicious dressing. And in a similar way, we at Zapata Computing view quantum and machine learning like being like oil and vinegar, where yes, they are separate fields by themselves, but there are times and specific ways in which the two fields can come together to potentially enhance some solutions to interesting problems. And we note that QML is a relatively new field with a lot of new questions and myths that come on their own. So today I thought we could spend some time approaching some of the said myths and hopefully debunk some of them. And so before we begin, I wanted to kind of get a sense of the audience by looking at this QML Venn diagram or landscape, if you will. So we're going to start a poll in just a few minutes, but essentially, if you see yourself more in the quantum computing side of the Venn diagram, or your interests lie in quantum computing, you should vote in zone A. If your interests are, or your research is in QML, you should vote in zone B. And if you're from classical machine learning background, you should vote option C. And if you're in none of these fields, you should vote D. So if you could just spend the next couple of minutes filling out the poll. So I think, yeah, if you can fill out the poll, that'll be great. Oh. Where here are the three options, or four options, sorry. And so Caitlin or Marta, could you let me know when the poll has been completed? Because I can't view it from the presenter mode.
I think okay. The poll has been completed, Hannah, and I can tell you that the audience there is 42 people in quantum computing, or 42% in quantum computing, around 17% in QML, 14% in machine learning, and 26% in other.
Oh, that's very interesting. So that we do have a pretty diverse audience, and it turns out that that's somewhat similar to actually, so we did the same exercise as Zapata Computing to get a sense of where everyone's interests and research lies, and we had a pretty similar, I think, percentage as well at Zapata, where, for example, I see myself more in the quantum computing side of the Venn diagram, although over the years I've been inching closer and closer to the QML zone of the Venn diagram. But folks like Marta and Caitlin, they've been really directly working within the QML research and applications. So that's really cool. And so with that, we're going to dive into the QML myths. And so the first myth that I wanted to go over today is the idea that you need to be an expert in both machine learning and quantum to significantly contribute to QML research or applications. And of course, it's great if you're an expert in both, but I don't think that's necessarily a must. And in order to debunk this myth, I thought I'd go over my personal path to QML research. So when I started my PhD, I started studying the variational quantum eigensolver, or the VQE algorithm, where I was trying to estimate ground state energies of different molecular systems. But that was also around the time in which a lot of near-term algorithms for QML applications were being developed. For example, the variational quantum classifier, which was actually one of the main developers was Maria Schultz, who gave a talk earlier this morning, as well as a scheme for compressing quantum data, which is called the quantum autoencoder. And so around this time, when I was really interested in these near-term algorithms, I had a chance to step back and look at all of these algorithms together. And that's when I realized that while these algorithms seem very different or different in terms of the tasks that they're trying to address, they share a lot of the same components or the backbone structure to these algorithms. And one of these core components of the algorithms is the use of what is called the parameterized quantum circuit, or PQCs. So you can think of PQCs as being a tunable version of a quantum circuit where there are particular parameters you can vary the values of in order to generate some interesting or relevant states that encode the solutions to your problem. And so in the case of QML applications where there's some component of learning, these circuits are also known as quantum neural networks. Also, I forgot to mention that we will have a Q&A session at the end of this talk. So if you have any questions about any parts of the talk, please put your questions in the chat. And so over the next couple of years, I spent a lot of time trying to think about these PQCs and better understand them. Specifically, number one, how to better design these parameterized quantum circuits. So for example, if you're given, say, a QML algorithm, a variational classifier algorithm, and you have a tool set of, say, 5 to 10 circuits at your disposal, which circuit should you choose for your algorithm and why, without having to run your algorithm 10 different times with each of the different circuits? And so in order to answer this question, my work as Zapata involved coming up with some theoretical descriptors or quantities that you can pre-compute for each circuit in order to estimate the relative capabilities or expressive powers of different circuits. And that way, you can have a more guided selection process for your PQC for a given problem. And another component of these near-term quantum algorithms is the actual tuning or the optimization of the parameters of your circuit. And towards that end, our recent work as Zapata came up with an algorithm that essentially allowed us to optimize circuits that have thousands of parameters. And so in this way, while I didn't personally start from a classical machine learning background, and I'm no expert in that field, these works over the past few years have really contributed to quantum machine learning research. And so just to say, this is one example where I wasn't necessarily an expert in both machine learning and quantum, but still got to contribute to the field. And the next myth is that the idea of trying to enhance machine learning with quantum should always be justified. And so to clarify this statement, what I mean is when you're trying to enhance machine learning with quantum, you shouldn't quickly scrap ideas just because these ideas don't immediately prove or point to or show this idea of quantum advantage. My thought is that because QML is a relatively new field, a lot of the research there should be exploratory to some extent, where you don't always have to have the perfect justification for trying something new with quantum and machine learning. And in addition, I like to note that a lot of recent QML studies with solid theoretical results, such as Google's recent work that really identified a regime in supervised learning in which a quantum advantage is likely to be shown. Studies like these, they came about because of all the earlier exploratory studies in the beginning in QML. So just to say, again, trying to enhance machine learning with quantum doesn't always immediately have to lead to this idea of quantum advantage. And so with that, I'll pass the torch to Caitlin Gilly, our quantum applications consultant, who will also go over a couple of myths.
Thank you, Hannah. And thank you all for being here today to come hear us debunk these myths in quantum machine learning. I think it's amazing that we have such a diverse audience in the crowd as well. And again, like Hannah was saying, I think we all come from a similar background in that way where, some of us started in quantum, some of us started in machine learning, and then slowly kind of merging towards the two. And so in my next myth, I want to talk a little bit about my background as well. And so the myth that I'm going to be discussing is quantum is always a large part of the algorithm or the quantum machine learning algorithm. Hannah, if you'll just go to the next slide. Thank you. So in order to debunk this myth, I'm going to share a little bit about my personal path as well. And so my kind of path to quantum computing started before my path even to quantum physics. In my undergraduate degree at Stevens Institute of Technology, I studied physics, but I actually, before I even took my first quantum physics course, I learned the basics of quantum computing at a summer research fellowship at Keio University in Japan. And so while I was at Keio and learning kind of the basics of quantum computing, and ended up really enjoying the kind of the start of the field and where it was going, this was a couple of years ago. From there, Hannah, if you'll go forward, then, of course, I went back to my university and dived deeper into some of the more quantum mechanics and the computer science of it all. And from there, that's when I started thinking more about machine learning and one of the professors that I was working with. And so in a work that I did in my undergrad, as we looked at a specific algorithm for a quantum k-means clustering. And so for, kind of a classical k-means clustering standpoint, you have, maybe a bunch of data points with very high feature dimensions, and you want to be able to just have some sort of distance metric to be able to cluster these data points together. And so you really essentially want to be able to see, are these points similar? Are they far apart? To be able to cluster them. And so what we could do is we could actually use a quantum distance measurement. We could use a swap test and encode our data points into our qubits to be able to use this as a distance metric. And all of the rest of the parts of the algorithm were actually classical. And so really the only kind of key quantum component to this algorithm was the fact that we had this quantum distance measurement and this encoding. But the rest of the optimization and everything else was classical. And so part of the myth that I want to debunk here is, that quantum always has to be the large part of the algorithm. And quantum doesn't always have to be a large part of the algorithm. It could just be kind of a trick or something that you can do to the algorithm to show an enhancement in accuracy or an enhancement in speed. Hannah, if you'll go to the next slide. And then so the other myth that I want to debunk is that quantum noise in today's hardware is always a roadblock. And I want to share a little bit about my experience at Zapata as well, and my experience with kind of getting into more of quantum neural networks with machine learning. And so, we have these NISQ, noisy intermediate scale quantum devices. Right now, I'm actually at the University of Oxford in a PhD program that focuses on trapped ion qubits. And so I've seen kind of firsthand, some of the noisy devices that we do have and that we're improving and we're enhancing. But with these noisy devices, we need to take into account that we might need shorter depth circuits and we have limited error correction. And like Hannah was talking about with these parametrized quantum circuits, they could be very important for, these algorithms that we can actually do on today's hardware. And so this really, has led a lot of scientists to ask the question, what can we do with noisy hardware? And machine learning is a huge application. It's why we're here today talking about quantum machine learning. It's a huge application for what we can do with these quantum computers today. And I want to specifically talk a little bit about generative models, because classical generative models are seen to be a type of machine learning that is it is growing a lot closer to full artificial intelligence. And it's a very promising candidate as well for quantum enhancement and quantum advancement. And so, Hannah, if you'll go to the next slide. And so just to talk a little bit about what a generative model is. And so these models essentially aim to find an unknown probability distribution given many samples to train on. So essentially, if you have this training data of all of these people, all of these faces, and so you kind of input this training data into your generative model, you have some random noise in this generative model as well. And the whole point of this generative model is that you want to find P of X. So you want to find the probability distribution from the underlying probability distribution from these samples that you're feeding it. And then in the end goal is that you'll generate a new sample. And so you'll notice that, the woman's face that we see here was not in the original training set, but it's similar in the way that it is a face a face like others in the original training set. And so one of the entire goals of this generative model is to be able to produce unseen data, but data that is similar to your data in the training set. And Hannah, if you'll go on to the next slide. And a really promising candidate for quantum advancement are these quantum generative models. And there's a lot of different kinds. There's quantum GANs, there's quantum circuit-borne machines, where here is an example of a quantum circuit-borne machine. And in a recent work from Zapata as well, which is what we call our QEO paper, or Enhancing Combinatorial Optimization with Quantum Generative Models, they demonstrate that this can be done with financial asset data sets from the S&P 500. So they're really showing this kind of practical generation as well. But here, what you can see is that, if you have this training set, here it's bars and stripes. If you have this input training set into this quantum neural network that Hannah was talking about earlier, what we can actually do is we have an input distribution and a target distribution, and we can use the quantum neural network to be able to optimize our parameters such that we can minimize a cost function, and we can output a distribution from our QCBM, our quantum circuit-borne machine. And from the output samples, we might be able to generate new samples that weren't in the original training set. And this is something that the QEO paper, again, shows with the financial data sets. And so what I really want to kind of bring back here is that while there are roadblocks with hardware, we have a lot of ways to go. Machine learning is still one of those kind of core applications, especially even overlapped with finance, overlapped with pharmacy, overlapped with a lot of other applications that we can use on today's hardware, even though that there is noise in today's hardware that we're working towards these fault-tolerant quantum devices. And so with that, I'm going to turn it over to Marta Mari, someone who I actually work quite close with at Zapata on improving the generalization of these quantum circuit-borne machines and looking into it a lot more. And so I'll turn it over to Marta to talk to you about some more myths in quantum machine learning.
Thanks, Caitlin. I hope you can see my screen. Okay, so let me start. Let me know if there's any problem with visualizing the slides. Thanks, Caitlin, for introducing me, and thanks everybody for being here. Let me just start with my first myth in quantum machine learning, that is that quantum is the answer to everything. So as you may know, lately there has been a lot of progress in the field of quantum computing, both on the hardware side and of the software side, and these led to a growing interest in quantum technology across many businesses and companies and industries. Therefore, oftentimes it happens that a company comes up with a list of hard tasks that they have, meaning like time-consuming tasks that they have to solve, or expensive and that they want to speed it up, and things like that. And so they come up with this list, and then they just expect quantum to be like that magic element that you add to the solution of the task, and that solves everything better. And so I like to call these quantum speed up idolatry. So somehow the idea is that if you add just a pinch of quantum to your problem, then you're going to improve it anyways. And in fact, this is actually not the case, because not only hard problems don't necessarily benefit from a quantum approach, but also it's not straightforward at all to cast your problem in a form that is quantum friendly. So even just saying, like, in machine learning, adding a quantum part to the algorithm, this is a non-trivial task, because you really have to come up with an idea to put this quantum component in a way that is really useful, and it's not even easy to cast your problem in that form. And so to get to this point, I want to make an example of something that I have seen directly with this kind of issue of reformulating your problem in a quantum-friendly way. And so before getting into that, let me just say a little bit about how I got into quantum computing and quantum machine learning as well. So my background is actually pretty hardcore physics. So I got my master's at Università di Milano in Italy and I studied basically quantum physics and quantum many-body physics in my master's, and I was super interested, and still I am super interested and fascinated by the macroscopic effect of quantum physics, so especially superfluidity and superconductivity. I found these like really fascinating, and the way I've been studying these complex systems was by computational approach, both theoretical and computational approach. And so in this context, for my master's thesis, I used this computational approach to study the ground state properties of a quantum spin system. So basically, we wanted to study these relatively easy quantum systems to understand properties like the ground state energy, the magnetization, and these kind of things. And in doing so, the approach that we used was using a neural network to model the wave function that is the state of the system, and try to optimize these and come up with the value of the energy. So the whole point of me mentioning this is that this point of my master's thesis is where I met machine learning directly for the first time, and also where I realized that simulating a quantum system with a classical machine, with a classical computer, is not straightforward. It's not easy at all, so much so that we had to use these complicated and advanced techniques such as machine learning for, as I was saying, a relatively easy system. And therefore, this is where I realized that really simulation of quantum system is challenging. And I mean, I'm not the first person who realized that. In fact, Feynman in 1980s came up with this question, and this was actually the first idea of quantum computing. And in this paper, he asked this question: can a quantum system be probabilistically simulated by a classical universal computer? And he says the answer is certainly no. So really having touched directly how difficult could be the quantum simulation, and like having been introduced to this perspective and idea of quantum computing, I really thought there was something interesting to me, because I'm really interested, as I was saying, in quantum simulation, and therefore having a tool that allows us to study that, I mean, better, but also like really allows to study that in certain cases where we don't have any other tools. I found that really interesting, and so that's why I decided to go into quantum computing. And so as you can see here, like there's quantum physics, there's machine learning, and there's quantum computing, and everything kind of like blended together, and then led me to join Zapata. And so now to go back to the myth, what I've been working on in my first year at a company was this project related to finance. And particularly, we were interested in solving a risk analysis kind of task, and in a collaboration with our customers who were a financial institution. So the point is that for banks and financial institutions, the problem of including the computation of the risk when computing the price of a financial instrument is pretty important, in the sense that there are also some regulation that force them to include these analyses in their pricing strategy, especially after the financial crisis of the late 2000s. And so this is like something that they can't, they inevitably have to do, but at the same time, this is kind of problems pertains to a particular category of problems which are hard and computationally expensive. Therefore, it's very important from their perspective to come up with a strategy that allows us to like optimize and make this the solution of these tasks more efficient. And so what we did was to try to cast this entirely classical problem of computing a price into a form that was quantum friendly. And so most of the project was actually spent in coming up with a reformulation of the problem in this quantum approach, and coming up with a circuit that could actually solve the problem, and also taking into consideration the limitations that we have nowadays on the hardware. So like a NISQ-friendly approach. And honestly, most of the project was actually spent in tuning these components in the circuit, coming up with these like the best way to assemble them and all these kind of things. And I found these like very, very interesting and challenging as well. So this is like to stress the point that it's not straightforward to find a way to introduce some quantum approach into your problem. And I just want to add one single thing here, is that, as you can see, there's this GP component, which is a quantum machine learning component that we used in the reformulation of the problem. And this is something that I actually, I was focusing on this, and I realized that some questions came up, and they're still open to me to try to understand what are really the capabilities and the limitations of this component. And so what happened is that after the project, I started also with Caitlin, we started to study like more in depth this kind of component. And this is just to say that, as Hannah was saying, some questions just come up while you start an exploration of a particular model, and then you can continue and let curiosity drive you in exploring that. And then eventually, who knows where we will get. But I think curiosity is like the driving force for me into this, to navigate into this field. And another small thing is that, I said that it's not straightforward to find a way to introduce some like quantum component in a classical problem, but when you actually manage to incorporate a quantum component in a smart way in your algorithm and in your problem, then some like astonishing results can be obtained, in the sense that here you can see on the left there are so the problem that one could have is trying to generate images. So similar to what Caitlin was saying about the generation of faces with generative models. So we have a kind of a similar result, but instead of generating faces, we were focusing on generating handwritten digits. This is kind of a well-known and widespread studied data set for generative models. And the idea is that we enhanced a classical model using a quantum component, especially namely the QCBM that Caitlin was mentioning before, and enhancing our classical neural network with this quantum component, we were able to improve the results that were there for a quantum generative model before our paper in last December. And so here on the left, you can see the state of the art before our algorithm, then what instead we were able to obtain. So the point is that when you are able to incorporate in a smart way or in a good way your quantum trick, your quantum magic into your algorithm, that you can really enhance the performances of your algorithm. And so this is just to say that it's true, quantum is not the answer to everything. It's not the easy answer to everything, but can really be very helpful. Otherwise, I wouldn't be in the company and in the field. So I just wanted to stress this as well. And then let's go to the second myth. The second myth is that quantum computing is just waiting for the hardware to be ready. So sometimes when my friends ask me what I do, and I say like I work for a company that develops software and algorithms for quantum computers, they just like react saying, well, quantum computers are not there yet. So what's the point in developing something or some tools for a technology that we don't have yet? And I mean, I've been asked these questions a lot of time, and I actually think that we're not just waiting for a technology to come, because we are not even sure of what we can do with that technology once it's going to be here. So it's not that we are just waiting for Ferrari to come, and we're just like, but we know everything about it. We know how to drive it. We know what are the maximum speed that we can get. We know everything. No, like we are waiting for something which allows us to go faster in many senses. But we still need to learn how to drive it and how to really boost use these new machines. And so like being in the field right now and being in especially into the quantum software domain allows us to come up with proof of concepts, with ideas, with new algorithms and new tools that we can use to really understand how to make the most out of the machine once they will be here, but also will also give this kind of progress right now could actually give some insights in what are the bottlenecks that we have, what are the specific parts of the hardware that we would need to be more careful about in order to get like a specific advantage or a specific boost of performances. So like it's kind of a conversation and a dialogue that I think it's very important to have already today, and just not, well, it doesn't make sense to wait like until everything is going to be ready. So I like the fact of like being very challenged and like on this by this conversation between hardware and software and research as well. And so why does it make sense to have quantum software, to make a quantum software effort right now is because in this case, in this way, we have a testing ground that we can use to, come up with new algorithm, test ideas, and we have the tools to do that. And eventually, this will give some insight and will give a path forward, even for the hardware development as well. And I think we really need this because if you think about a company, I think before investing and make like large investments in quantum computing technologies, they are kind of interested in seeing if these can actually bring any advantage or any revenue to them. And therefore it makes sense to start right now to see if, this investment could actually be intelligent or helpful at all for them. And so in the same spirit, since we don't exactly know what will be the hardware that will be the first, full quantum computer with like error correction and everything. We don't know, like it's going to be ion traps, it's going to be superconducting qubits or photonic qubits, whatever. We don't really know right now. And so the strategy that we are using at Zapata is not to choose a particular framework or a particular, quantum computing paradigm, but like being able to use them all and orchestrate across them all in such a way that we can, test the different things. So in this spirit of like having a testing ground for algorithms now for like in vision of the future, this is like the approach that we are having, and what we are building, that is our platform Orchestra, like makes us possible to easily switch between these different frameworks and allows us to like do research kind of a easy way across the different platforms. So just to conclude, before we go into the Q&A session, just let me briefly remind you what are the 6 myths that we talked about today and we debunked. So first of all, you don't need to be an expert in both quantum and machine learning to contribute to QML. And exploratory and numerical studies can help progress QML. in the sense that, as Anna was saying, like you don't need to justify everything before you start doing that. Then the third myth that we debunk is that quantum doesn't always have to be a large part in a QML algorithm, but can just be a trick. And fourth is that quantum noise in today's hardware may be helpful for particular tasks, so we can take advantage of what we have right now to solve certain particular problems. And then the last two is that quantum is not an easy answer to every problem. And in fact, coming up with a quantum formulation of a problem can be challenging. But when you do, you can get interesting results. And then at the end, the last one is that there are ways to progress quantum computing in addition to hardware development. And software development will also be the key towards realizing quantum advantage. And so these are the 6 conclusions that we wanted to, the 6 messages, let's say, that we wanted to communicate to you. And if you have questions, you can definitely ask them in the chat, and also reach out to research@zaparacomputing.com for like a more in-depth discussion. So thanks, and I'll leave it open to questions.
Thank you. I will try to moderate the questions. So we have a question from Kirsty Gardner. She is asking, question from a newbie: if you have an algorithm for a problem, will it work on all frameworks hardware, or will it need to be adapted for each system?
Yeah, so I can try to answer this one. I think that's a great question. I think that it's the latter, where if you have an algorithm, for example, one way to realize these quantum algorithms is through a quantum circuit. And so you have this somewhat of an abstract quantum circuit that you write on paper with all these fancy gates. And when you run that on a quantum computer, it should theoretically give you a solution to the problem. But on actual hardware, depending on the architecture, each device has its own supported gate set, as well as the actual device connectivity. For example, which qubits can directly kind of communicate or entangle with each other. So there is this intermediate step of having to take that abstract quantum circuit that you designed and kind of translate it down to a lower level kind of circuit language, where then at that point, once it's compiled down to something that can be executed on specific hardware, then you can run your algorithm on a particular hardware. But so there is that intermediate step that you need to do in order to, say, adapt to the particular hardware system.
Excellent. We have another question from Alona. What are the current trends in QML research?
Well, I'm not sure about all the current trends, but I'd say maybe one trend that I'm noticing, especially in the earlier works, is that, so I went over this idea of parameterized quantum circuits, and in the beginning, I noticed that people just proposed a very specific circuit design to run on their QML algorithm or some near-term quantum algorithm that uses these parameterized quantum circuits. But I think over the years, people started realizing or tried to ask the question of, hey, but why am I using this particular circuit? And a broader question is, well, how do you then, given a problem, design an effective circuit that's not just an arbitrary circuit design? So at least I think that seems to be one of the trends where people are now trying to better understand and better design these parameterized quantum circuits or quantum neural networks for near-term quantum algorithms. So that's only one of the trends, though. I'm not sure. Anything else? Marta and Caitlin?
Yeah, I think that there's also these, I mean, it's related to what you said, the trend of like understanding expressibility and capabilities of quantum neural networks against classical neural networks. So like trying to really open up a little bit the black box of these machines that we're, or these models that people use, and trying to understand what are actually the the points in the quantum formulation that can that are there that are not in the classical part that can actually enhance algorithms and solutions. So I think this is something particularly interesting that also opens up the question of other two other questions that are open, I think, are the generalization capabilities of quantum models against classical, and then the other one is the trainability of quantum circuits against classical models, because obviously, there are a lot of power. There's a lot of computational power in the classical domain for neural networks optimization, whereas for the quantum computer, we're also limited by a certain number of qubits and a certain technology on the hardware, and therefore, we are not at the same level. And there has been a lot of research already for the past years for classical machine learning and deep learning, and we're still at the very early stages in the quantum part and the quantum correspondent part. So we still need. This is pretty open, and I think these are all interesting questions, and I hope we can get to some new steps in these directions.
Okay, thank you. This is a difficult question. If you each get a time machine and you travel 5 years out into the future, what would be the biggest achievement we see for QML 5 years out?
I think parts of this have been kind of hinted in literature already, but I think a big achievement in the next 5 years would be more solidly identifying problems or regimes in different subfields within machine learning where we can prove that there is a quantum advantage. So like I mentioned before, there has been a Google paper very recently that identified particular regime in supervised learning that they're expected to have quantum advantage, but having that as kind of a broader goal across a lot of more tasks in machine learning or quantum machine learning, I think would be very valuable.
Yeah, I'll bounce off of that, Hannah. I think bouncing off of the idea of looking for a quantum advantage in a lot of these different industries, and maybe I'm a little bit biased towards generative modeling as well, but I think generative modeling is a very promising QML algorithm or model, a generative modeling circuit like a QCDM or like a quantum GAN for being able to ultimately produce real value. I think also hopping off of what Marta was saying before about generalization, seeing if these models, how they generalize, and then using not only this being able to produce new unseen data, but new unseen data of value. So I think 5 years in the future from now, one of the most impactful things is going to be all of these different problems that produce the real value within, whether it's pharmacy or it's financial applications, or whether it's sustainability. And so I think it's really seeing kind of this value add for a lot of these different algorithms in industry.
We only have 1 minute left, and I know there's more questions coming in. If you want to continue this conversation, please feel free to send an email to research@zapatacomputing.com, and we will try to answer as many questions as possible. Thank you, Marta. Thank you, Hannah. Thank you, Caitlin, for debunking the myths in quantum machine learning. And thank you to the organizers of this event, Women in Quantum Summit. Thank you.